We are going to begin Physics 261, looking at the electric field. So a field has a value at each point in space. You could take a thermometer and you could measure the temperature at every point in space. That is an example of a scalar field because you have a value at each point in space, but there is no direction associated with it. We are going to be looking at vector fields in this class. And one example of a vector field is the gravitational field. And the gravitational field is represented by the little g, which you are familiar with from previous physics course. But now we're going to write it as a vector. And if you are close to sea level on Earth, then little g has a magnitude of 9.8, but if you are not on Earth, or if you are not close to sea level, then you would represent little g using capital G, which is a constant, and I'll tell you what that is in a moment, and m, which is the mass of the object, which is creating the field, and that is divided by little r squared, where little r is the distance from the center of the massive object, which is creating the field, to the point where you are measuring the field. This is a vector. It's pointing inward in the radial direction, so we're going to use a unit vector r to indicate the radial direction, and it's pointing inward. So we're going to put a negative sign there. So if we have a large massive object, such as the Earth, if you are closer to the Earth, then the field is stronger because little r is smaller. So little r goes from the center of the large massive object to the point of interest. The field is pointing inwards. As you get further away, the field decreases. If you are at the same distance r from the center of the large massive object, then the magnitude should be the same and the direction always points inward. So this is the gravitational field, and capital G is a constant. It is equal to 6.67 times 10 to the negative 11. And the units for that are newtons times meters squared divided by kilograms squared. And we can check to make sure that those units work out correctly. If you remember from Physics 161, the force, which in this case would be the gravitational force, is equal to the mass of the object which is experiencing the force times little g. So if we take our gravitational constant here and divide it by r squared, which has units of meters squared, and multiply it by m, which has units of kilograms, that gives us little g. And then if we multiply that by kilograms again, we should get force, which has units of newtons. So if we take capital G and multiply it by a mass and divide it by a distance squared, that leaves us with newtons divided by kilograms. The meter squared cancels that out, and one of the kilograms cancels out. And if we multiply that by kilograms again, this would have units of newtons per kilogram multiplied by kilogram, and that gives us newtons. And since G, we know, has units of meters per second squared, a newton times a kilogram is equal to meters per second squared. Okay, so we can take our field and we can multiply it by a mass to get the force on that mass. So this capital M, this is the mass of the object which is creating the gravitational field. So if you're talking about you standing on Earth, capital M would be the mass of the Earth, and the field exists at all points in space, even if there is not an object at that point in space. The force can only be exerted if there is an object to exert a force on. So little m here would be the mass of the object that is experiencing the force. So if you're standing on Earth and you want to know the force that gravity exerts on you, here this would be the mass of the Earth. And then if you want to know the force, you would take the field and multiply it by your mass. And since little g was pointing in the negative r hat direction, the force would be pointing towards Earth, which we know. So that is an attractive force. Okay, now we're not going to spend a whole lot of time talking about the gravitational field in this course, but it will pop up again later when we look at the electric potential. But it's useful to look at now because the electric field, which we are going to be studying, is very similar to the gravitational field. Okay, so that was all for the gravitational field. Now we're going to look at the electric field, and this is actually on page 5 in Spiral Physics if you want to look it up there. So the electric field is equal to a constant, K, which is Coulomb's constant, or also called the electrostatic constant, times Q, which is a charge, divided by r squared, just like we saw for the electric field, where this is the distance between the charge and the point in space where you're looking at the field, and that's pointing in the r hat direction. Unlike the gravitational field, there's no negative sign in front. Also, unlike the gravitational field, you could have the field either pointing inward towards your charge or outward away from your charge, and that direction depends on the sign of the charge. When we have mass, we only have one type of mass, but when we have charge, the charge can be positive or negative. So the electric force can be an attractive force or a repulsive force, depending on the signs of the charges that you have. Okay, so K is a constant, and that is 9.0 times 10 to the 9th newtons times meter squared per coulomb squared. So if you compare the electrostatic constant to the constant capital G here, you can see that the difference that we have in the units is here we had kilograms squared in the denominator, and here we have coulombs squared in the denominator, which is what the capital C stands for. So the charge Q has units of coulombs. And if we want to calculate the electric force, which we'll be doing in the next section of the book, the electric force, so let's call it F sub E, so we don't confuse it with the gravitational force, that is Q times the electric field. So here we had mass times the gravitational field giving us the gravitational force. Here we have charge times the electric field giving us the electric force. This Q is not the same as the Q here, so if you want to take the electric field and put it into our equation here, because they're not the same charge, we'll call one of those Q1 and one of those Q2. So that would be what you get if you take this and put it in here. It does not matter which one is Q1 and Q2. If you have just one charge here, like we did with the Earth here, if you have just one charge creating your electric field, that electric field exists at all points in space, could either be pointing outward or pointing inward, depending on the sign. If Q is positive, then the direction would be in the positive radial direction, so pointing away. And because the electric field is inversely proportional to r squared, which is the distance from the center of the charge to the point of interest, the field is going to get smaller as you move away, just like it did for the gravitational field here. If you were to look at the moon here instead of the Earth, because the mass of the moon is smaller, if you were the same distance away from the center of the moon as you were from the center of the Earth, r squared would be the same, but because the mass of the moon is smaller, the gravitational field would be smaller. Okay, and if you're the same distance away, the field at that point would have the same magnitude as what we had there. Okay, now to have a force, you have to have another charge at some point in space which is experiencing the force. And so if we did this, Q1 and Q2, this charge has a field, and you could find the value of that field at this location where Q2 is. Or you could also say Q2 has a field which has some value where Q1 is, and you could either use the field from Q1 here and multiply it by charge 2 to get the force that charge 1 exerts on charge 2, or you could look at the field that Q2 has here and multiply it by charge 1 to get the force that charge 2 exerts on charge 1. But as we know from Newton's third law, those forces should have the same magnitude but the opposite direction, so it doesn't really matter which one is Q1 and which one is Q2 here. And if these two charges are both positive, then these charges will repel each other, so that will be a repulsive force. If the charges are both negative, we have a negative times a negative giving us something positive, so that will also be repulsive. If one is negative and one is positive, then that will be an attractive force. And if you go back to the picture here, the radial direction is always pointing away from the charge. So if you take another charge and put it here, if it's a positive charge, the sign stays the same, so radial is pointing away, so that force will be pointing away from this charge. If it's a negative charge, then it will point in the opposite direction of r hat, which is in towards this charge here. Okay, so we're going to stop here for now. Next, we're going to look at some examples from the book.